Okay, now you know that it's the videos of the lecture are available on my website. Now let me go back to my website. Let me open it and then I share the screen in order to, just 1 second, in order to stay on the same line. And of course you may decide to follow on my screen or to open the website on your PC in local mode. Now let me share the screen, 1 second. Here we are. Okay, so you see the first tab. Just 1 second. I want to open also Teams on the phone so I can check what you see. I want to make sure that you see what I believe you are seeing. So it's here. Just give me 1 minute. Okay, and then should be okay. Just let me see. Okay, everything is fine. Good. Now let's click on the first tab, and which brings you to the tutorials. And as you may remember, we are at the second link, Sustainability in the 21st Century. Let's click on it and let's go down where we got last time. Just 1 second, I get the PowerPoint, which is better. Okay, and then here. Okay, let's, just 1 second. Okay. Be patient, I have a new version of Office and then I need to, okay, let me go down. 1 second. Okay. Still, I cannot visualize it in. Give me 1 second. I try to visualize the presentation on this correct screen, so I don't think I can succeed in this way. So let me share in a different way. Okay, here we are. Let's go down. I think we got to this slide last time, which still it's very, very tiny. Let me see. But okay. I think we got to this slide. I'm not sure if you see it in full size. I hope you can read it because I am sharing a screen that is of a small size, and I suspect that you may see it in a reduced. So give me 1 second. I want to make a further attempt to get it in the correct way. Give me a few seconds. So let me share the screen. Okay, it's already shared. So let me do like this. And then let me 1 second. Still. Okay. Okay, now I am okay. Let me see. Okay, this is perfect now. So good. As I said, we closed the last lecture with this slide. I suggested to you to have a look at it, at the information that is contained herein, which gives an idea of the water footprint. The water footprint is basically the amount of water that is used by each country, including the virtual water transfer, which is the volume of water that is transferred between countries through the import-export of goods. And so when we import food, we export food. Actually, we import virtual models. So this is a concept that is relatively new, which is extremely interesting because it gives us a means to transfer water. We said that the problem in water resources management, one second, I have a look at the chat because I see that there are comments here. No, perfect. As I said, the problem in virtual water in water resources management is the distribution of water. We have enough fresh water available for everybody, even in front of a future predicted increase of population. The problem is that we don't have water in the right place at the right time. And it is a problem because moving water is not easy. Water is heavy. And virtual water transfer is something that recently emerged, which gives an opportunity to move water between countries and in a way also to store water in the virtual form in order to also solve the problem of the odd distribution in time. Okay, now let's move forward. And this slide shows the global water footprint by sector, which means the use of water at the global level, which is for 78% used internally, which means that countries, in order to produce food and produce, let me have a look at the chat one second, okay, produce food, produce industrial products, and produce domestic products, these countries at the global level use internal water for 78% of their needs, while the external water footprint amounts to 22%, which is the virtual water associated to imported goods, total imported goods. If we explode this 22%, we see that it's composed by 20% out of 22 by agricultural products, and the remaining 2% is given by industrial products. So this means that at the global level, we move 20% of the total water footprint, of the total use of fresh water. 20% we move it by trading agricultural products, by trading food, which is something that it's really relevant. It gives an idea that the virtual water trade covers about 1/5 of the total water use. So you see that indeed it's something important. Now let's focus on freshwater availability and freshwater availability, which is something, just one second, I want to keep the chat on the second screen, otherwise okay, perfect. As I said, global freshwater availability is our reserve, and I think it is important to have an idea of what volumes we are talking about. Please keep in mind that this is it's a figure that just depicts volumes, and I will explain later what I mean. I think only depicting the volume only getting an idea of the volumes does not give a comprehensive view of water resources availability, but I think it's a good way to start. As I said, I will explain later what I mean. If you look at the total global water, you see that more than 97% is salt water, because you see that oceans contain, store 96.5% of total global water on the Earth system. So atmosphere, Earth crust, Earth interior, the total volume of water is for 96.5% in the oceans. Keep in mind this order of magnitude. If you add the additional 0.9% of other saline water, you get to more than 97%. So the fresh water, which is the water that we can use, is only 2.5%. Now let's look at the second column, the middle column, which is an explosion. It's a zoom on the 2.5% of fresh water in the first column. It is zoomed out in the second middle column. You see that of this 2.5% of fresh water, we have groundwater accounting for 30%. We have glaciers and ice caps accounting for almost 70%. And then we have only 1.2% of surface water, other fresh water, which means that, again, if we look at fresh water, which is the water that we can use, we get most of it concentrated in glaciers and ice caps, and 1/3 of it in groundwater. The surface water is only 1%. Just keep it in mind. Now let's explode this 1.2% in the third right column. And you see that there is a 69%, which is taken by ground ice, which is different from glaciers and ice caps in the middle column. Ground ice means frozen ground. So ground ice and permafrost takes more than 2/3 of the 1.2%, which is 1.2% of the 2.5% of fresh water. Now, we have lakes that are placed above the ground ice and permafrost. They account for 21%. And then you see soil moisture, 3.8%. You see swamps, marshes, 2.6%. Rivers, 0.49%. And atmosphere, 3%. Living things, living organisms, 0.26%. Now, let's focus on rivers, which are an important source of fresh water for human use. They are 0.49% times 1.2% in the middle column times 2.5% of the global water, which means that rivers are nothing when compared with the global water. But, as I said, they are an important source of fresh water. So you may say, what's the matter here? They are important, but if I look at the percentages, they are negligible. So what is hidden here? What is hidden is that rivers, the water in rivers is flowing, which means that it's immediately renewable. So you take 1 liter of water from a river, and then in the same place, you get soon, in a second, all the water flow immediately available. Okay? It is renewable. It is immediately renewable. And therefore, it shows that one thing is to take water from a river. One other thing is if I take water from groundwater in the middle column, the brown part. This groundwater, which is another essential storage that is used by humans, it is essential in most of the Western world. We get in most of our water resources from groundwater. The problem is that groundwater it's not immediately renewable. It may take 100 years to replenish an aquifer. A river, instead, it takes 1 second, which means that when we take water from the river, we are more relaxed than we take water from groundwater. So this explains why at the beginning, when I introduced this figure, I said storage is not comprehensive to provide a view of freshwater availability. We should identify storage plus water flow. And therefore, we would observe that in rivers, flow is really important. It's not the volume that is important for river, it's the flow. In groundwater, we have a higher storage, but the water flow is much more reduced because the velocity of water is more limited. Okay, now let me admit a couple of students that are getting into the room now. Can you please mute yourself? Thank you. Okay, and now let's move forward. In any case, please take into account these orders of magnitude in this slide. So you have to be fully aware that fresh water is only 2.5% of total water resources. And of course, this picture tells you that desalination may be an important solution to water scarcity problems. Of course, you may already know it, but there are still problems with desalination. We will see what the problems are. Okay, now, sorry, if you look at the, let's concentrate now on the spatial distribution of water resources. And the spatial distribution of water resources is more or less dictated by the spatial distribution of rainfall. And here you can see a video which was prepared by NASA about the spatial distribution of rainfall in the different months. It's animated video. What you can see from here is what we basically already know. Water is concentrated, rainfall and therefore water resources availability is concentrated into the tropics. And also we have a seasonal water resources availability in the northern hemisphere. And in particular in Europe and the United States, you see that there is a pronounced seasonal variability, which means that we have water there, but sometimes not at the right time, because we have more water during the winter and less water during the summer, but we need water during the summer for irrigation. And therefore the problem arises of the time distribution of water resources. This is something that we have to solve. As I said, our problem is given by the spatial and temporal distribution. Our problem is given by the distribution in space and time of water, which is not homogeneous in space and it's not stationary in time. Remember that when we talk about distribution in space, to mean a uniform distribution, we use the term homogeneous. When we talk about distribution in time, when we want to mean a uniform distribution, we say stationary. Okay, so when we say that the climate is non-stationary, it means that it changes during time. And when we talk about non-stationarity, we can use the term seasonality to mean changes that repeat themselves within the year. So the seasons induce, seasonality induce a kind of non-stationarity in the short term. Or we may use the term change or trend to mean a variation, a change that is irreversible in time, is not just due to inter-annual variation, intra-annual variation. It is something that is changing in the long term. So this is our problem that we have to solve. Okay, let's talk now about climate classification, which is something that it is related to the spatial distribution of rainfall. And let me now to give you an overall idea of the spatial distribution of climate over the Earth, let's focus on the Kopp classification, which is given by this picture. Now, the Kopp classification is classification of climates, of the distribution of climates over the Earth. Here you see that the climate is divided in 4 classes plus additional subclasses. The 4 classes are A, B, C, and D. Let's see what they are. So the A class is the tropical climate, and then there is a subdivision of the tropical climate in F, which means rainforest, M, which means monsoon climate, and W, which means savanna wet climate. The tropical climate, the A class, is in general, it's in general very wet. It's a climate that is dominated by rainfall. We have a lot of water resources there. And you see the distribution is of the tropical climate is concentrated around the equator. Perfect. Now, first, you don't have to learn these climates by memory. I think it would be enough if you learned the 4 classes. Tropical is the first one that we discussed. Now, the second class is B, dry climate. Dry climate is depicted in colors you see on the map, from red to orange, yellow, orange, pink. And it's a dry climate, as the term suggests. Less rainfall and very reduced water resources availability. You see the north of Africa, where most of the deserts are concentrated. You see the desertic part of Australia and other spots over east of Europe. Of course, the dry climate is where most of the let's say most of the problems related to water resources are. And keep in mind that water scarcity has, of course, economic implication. It means that scarcity is impacting the gross domestic product, GDP is impacting the economy, and is also water scarcity triggering political and social tensions. Remember that the water resources availability is dominant control on politics and societal development. And water scarcity may explain by itself most of the societal problems that we are experiencing in the world. It is a form of inequity because, of course, water is a very important resource. It's not it's evenly distributed, it's not uniformly distributed, and generates inequity, something that if we want to ensure sustainability, we have to resolve. Remember that sustainability is undermined by inequity. Sustainability and equity are tightly connected. Now we got to the second climate category. Let's move now to the third, the C climate category, mild mid-latitude. The C category is depicted with colors around, let's say, yellow, light yellow, green. It's a zone where the climate is favorable to human conditions. It is characterized usually by good water resources availability with a displacement in time that is dominated by seasonality. So it means that in these regions, water is easily available, but with easily, I mean that there are problems that can be easily solved due to odd displacement in time along the seasons. Finally, we get to the fourth climate category, which is the dry climate, and the dominant color is dark blue gray, and it's a typical climate of the cold regions. It's a climate where usually water is available. The problem is that agriculture is difficult to practice because of the generally cold weather, and therefore here the problem is not lack of water. The problem is the fact that the low temperature makes the agriculture, of course, more difficult. So we have four categories: And I think it is, if you could remember them, tropical, dry, mid-latitude, mild climate, and dry climate. And understanding this climate classification is important. Keep in mind that this climate classification is climate is continuously changing for both natural variability and human-induced anthropogenic climate change. And so, of course, if you have a shift in the dominant climates, then you get the necessity to adjust to it. And adjusting means political changes, means changes in the societal asset, which are not a problem if change is a long-term process. So people have the capability, nature has the capability to adapt if the process is not too fast. When the process is too fast, you know, adaptation comes at the expense of conflicts, at the expense of problems, and at the expense of breaches to the equilibrium, which then needs to be reestablished through an evolution, which is, of course, if it occurs in a short time, it generates societal problems. Okay, now, distribution of water resources, it's similar to the distribution of rainfall. What I want to tell you is that these slides are taken from the FAO database. You see here there is written, if you look at the bottom right of the slide, that the slide is taken by the Aquastat database of the FAO. It's a very interesting database. There are updated pictures there. It's open access. You can go. There are a lot of data related to water. It's the data cover freshwater availability, water usage per each country, etc. And as I said, it is continuously updated. This picture refers to 2015. If you want to see the picture for 2020, you just have to go there. And if you have some time, I suggest that you try to get familiar with these global databases. And there are a lot of open access databases where you can get data related to water. And the list is very long. I may mention also the database of the World Bank, sorry, which gives information on the economy of the countries, gives information on the GDP of each country, gross domestic product. And if you put together at the regional level, at the local level, or the global level, the data on gross domestic products, water resources availability, distribution of rainfall, you get a lot of nice overviews on how the GDP is connected to resources availability, which is, it is extremely interesting. Keep in mind that these global data have been made available only recently. And I would say that the FAO database, the FAO database, is no more than 20 years old, which means that most of this information is still to be exploited. And it is an opportunity also for, I mean, if you want to focus on this subject like global distribution of resources, which may be water, but not only water, during your master degree thesis could be an idea that can be easily carried out, provided that you are familiar with the web, you are familiar with the PC, you are familiar with data management, because of course then you need to put this data into a software to make some elaborations, to study correlation, etc. It is not difficult, but of course everything that you know what to do, it's easy. If you don't know, of course, getting familiarity with the PC and the web takes some time. But this is another opportunity for me to stress the importance of getting familiar with the information and with the digital format of the information. Okay, now let's move forward, and this is again taken by the FAO database Aquastat. This is the proportion of renewable water resources withdrawn by each country. And you see that the darker the color, the higher the proportion of renewable water resources that is withdrawn, which means that when you get to the red, these countries are by necessity taking most of their renewable water resources already, which means that they cannot increase much their water withdrawal because, of course, there is a limit to sustainability. And where you see that the color is lighter, it doesn't mean that therein you have opportunities for sustainable development. It means simply that they are not taking much of their available water resources. But the reason is, if you look at Africa, the reason is that they don't have the means to take it in some cases. In other cases, like in the north regions, they don't have the means to use this water. So, I mean, the picture gives an overall idea of the limit to sustainability given by water resources usage, but there might be other limits to sustainability, which of course we need to consider. We are focusing specifically on water, but water is not only the one constraint, it's just one constraint to sustainability. There are other constraints that we need to explore. Okay, and this is the water withdrawal per inhabitant, which shows how much water we use per capita. And again, where you see the darker color, it means that in those countries, people are using a lot of water. And keep in mind that the water usage is directly connected to wealth, to societal well-being, which it is a good thing, because when you see that countries are using a lot of water per capita, it's a good thing in general. Of course, you need to consider also the problems that this may originate. So if the water is withdrawn and most of it is lost for leakages, etc., or inefficient distribution, of course, the fact that they are taking a lot of water doesn't imply that they can effectively reach a societal benefit. So again, this is only a point of view, which anyway gives an idea that matches with your expectation. And here it's the proportion of total water withdrawal that is used for agriculture. And again, this is another point of view, another picture. Keep in mind that these figures give you an information that it's not something that you need to learn or present at the exam. It is an information that anyway you need to store in your background, because it's, I mean, keep in mind that when dealing with water, you have to be very careful and you need to be very smart. And with one necessary condition for being smart is to use all the information that is available. If you neglect some kind of information when managing water, you are going to miss opportunities. So it is what I really would like to do by showing you these pictures is to give you an idea of the information that you may get from the web, the information that is available, which is interesting because it's global and allows us to identify global solutions. Because one thing that recently emerged is that it's not just enough to solve water problems at the local level. If we want to reach a sustainable configuration, we have to resolve the problem at the global level. So this is why I want to present this global information to you. Now, let me give to you an idea of seasonality. And we talked about seasonality because we said that it's an important driver of uneven distribution in time. Indeed, seasonality is something that it's really, oops, sorry. Okay, very good. Seasonality is something that we have to take into account, and it's something that it's particularly pronounced, as we said, in the mid-latitude climates. Here you get a picture over Europe of seasonality in stream flow, and you see that there are variable regimes. So there are regimes where the river flow has two peaks, one in winter and one in June, in spring, and the other one in the fall season. And this is typically a behavior of the continental climate. And there are seasonalities that express themselves with one peak only, which may be in summer in the Alps or maybe in winter in the south of Europe. Try to get familiar with these different types of seasonality, which is something that it's important to take into account when you study, as I said, the distribution of water flow in time. How is seasonality resolved? By storing water. Given that it's a local problem, it's a time shift problem, you don't need to move water in space to resolve the problem of seasonality. It's just enough that you move water in time. How to move water in time? First of all, you can operate at the local level, and you may operate by storing water, for instance, with artificial reservoirs. And this is a classical engineering solution. Again, with the artificial reservoirs, you don't move water in space, you move water in time. Now, let's first of all, with this presentation, I already moved to the next lecture in my website. So let me pass back to my website. You see that the lecture that we were talking about, sustainability in the 21st century, ended with this graph, which we already dealt with. Now, let me go back to the web page, and here, the third lecture is Sustainable Management of Water Resources. And you can see that it deals with what we are already discussing. I just want to make it clear that I passed to the next web page, and we are there. Okay, now, before I move forward, so we just talked about seasonality. Let me go back to the previous slide. Okay, before we move forward, I want to make some considerations. And the reason is that the description of the problem is concluded. Now, the next slide already talks about solutions in general, okay? And in general, without going into the details, and then we will go into the details. And so the first consideration that I would like to make, what I presented to you so far, is a description of the problem of ensuring sustainability. So we talked about uneven distribution in space, we talked about uneven distribution in time. Starting from the problem is precisely the philosophy that I want to adopt in this course. And then, as you may remember, I want from the problem to pass to a description of the solutions. And then we will consider the specific details of each solution, which requires a study of the underlying theory. Okay, so problem description is concluded. Before we move to solution, let me make a couple of additional considerations. The first one is climate change. So we talk about water, we talk of something that is strictly related to climate. Climate change is a problem. And climate change is something that you will have to deal with absolutely and unavoidably. It is a bit of a problem because we still know little of it. So climate change wouldn't be a problem if we already knew how it develops, how it manifests itself, how it's what are the possible solutions. Actually, we have still a limited understanding of the climate system, and therefore we have a limited understanding of climate change. This is a problem because also this limited understanding prevents us to gain perception of the solutions. Now, we will deal with climate change later. For now, just keep in mind that it's identifying the solutions to climate change is a task for the engineer. For now, keep in mind that it's a problem that needs to be considered from our perspective by focusing on the science. We don't have to focus on the politics. We are technicians. So our role is to identify solutions starting from the science. So when we talk about climate change and when you study climate change, the suggestion that I give to you, which in my view it's basic philosophy for a technician, is to focus on the science, to focus on objectivity. And then there are emotional implications, there are political implications. This is a task for other professions, for other administrations. We are technicians, we have to focus on the science. And you know, it's something that it's really important, because if you focus on the science, if you focus on the information, you get a perspective that is different, and it's more appropriate for designing solutions. And keep in mind that when you make a design, you as an engineer, you have a responsibility, which is also regulated by law. It's regulated by the law in force. You have legal obligations. And these legal obligations imply that you take a responsibility. Your responsibility is to provide a safe design, a design that makes the best use of the available resources. So in order to satisfy this legal obligation, you need to focus on objective science, objective technical guidelines. And I think this is not unusual to say this, because you know, when you deal with, in general, with topical issues today, global challenges like water, like climate change, like equality, diversity, and inclusivity, equality of opportunities, human rights. You have different phases of the problem. There is the knowledge behind it, there is the politics behind it, there is the economics behind it, and it is important that each profession takes care of their specific task with the best of the available knowledge, the best of the available culture and preparation, in this case, in our case, technical preparation. Okay, I mean, doing engineering is not a political matter. Engineering is a technical matter. Okay, now let's move to the solutions. So, I already mentioned a possible solution to water scarcity, and in particular to seasonal water scarcity, which is storage. Storage, increasing storage, falls into the category of increasing water supply, increasing water resources availability. And this is a solution that was used also in the past, in the history of humans. Keep in mind that humans always had the problem to secure water. And what they did usually was to increase the supply. When water was needed, they decided, they tried to bring more water to the field for agriculture, to the cities for civil use. And an example is the ancient Romans. They did a lot of infrastructures. They built a lot of infrastructures in order to move water hundreds of miles from areas of abundance, usually high up in the mountains, to their cities. And there are many other examples. So, And also the same solution was used for satisfying energy demand. People tried to move water at the local level, of course, and tried to store water when it was abundant in the seasons, during the seasons where water was abundant, to save it for the use during the dry season. Which is fine, I mean, the only thing is that this solution has an environmental impact. And let's look at the costs of water supply. This is this slide is dealing with the economic impact of water supply. If you look at this slide, I think it is really interesting. It focuses on California and Arizona, let's say western of the United States. You see that these water supply categories are divided in two macro categories. On the left, you see, look in the bottom of the slide, conventional water treatment costs, and on the right, desalination costs. So about the conventional water treatment, you see the average cost, which is the third, counting from the left, the third column. This is the user average of all the 5 categories of conventional water treatment. It's the average cost in the USA of conventional water treatment. Now, if you look at each single category, the first on the left is groundwater. And the height of the bar is depicting the range of variability. So you see that groundwater, it is a bit costly. Okay. Brackish water, brackish means water with salinity higher than normal, but still much less than the salinity of the seawater, which means that with a weak treatment, you can use it. In Southern California, they have a lot of brackish water in the estuaries, which can be easily used. This is why the cost is reduced. On the other hand, brackish water is not available everywhere, but when it's available, if you think of the estuary is an easily accessible place. It's like a huge reservoir. So you can understand why it's in California, in the south of California, is available with a low cost. Now, the third column is the average. Let's skip it. Surface water for Southern California. It is, the cost is relatively high, but you have to take into account that this includes the cost of building reservoirs. When you don't need to build reservoirs, surface water usually costs much less than groundwater. For instance, in the region, in the Emilia-Romagna region here in Italy, I can tell you that the groundwater costs about twice with respect to surface water, because we basically take surface water directly from the river. For instance, think about water withdrawal from the Po River or water withdrawal from the rivers that flow down from the Apennines. This is water that is available by gravity, and therefore the cost is reduced. In the case of Southern California, it's a bit higher because, as I said, it includes the cost of reservoirs. Why is groundwater costly? It is costly because you need energy to pump it, because groundwater normally comes from aquifers that need pumping to be brought at the ground level. The last column in the conventional water treatment costs is the treated wastewater. It's still very costly. So, and let also me say that in most of the countries, it does not provide very significant volumes. The volume that we can take by treating wastewater in most of the countries is only a tiny fraction of the total water demand, which means that besides being costly, it's an intervention that is usually not very efficient, let me say. Also, keep in mind that you have byproducts by treating wastewater, which are muds, sludges, and the displacement of these byproducts is another problem. Now let's move to desalination. Desalination, you see that look at the global level indication, the global level column. You see that there is a range of variability, but still the cost is much higher than the other sources of water. Besides being an high cost, keep in mind that desalination today requires a lot of energy, which means also CO2 emissions. And you also need to displace, again, the byproducts, which are salty muds and salty sludges. It's not easy because, you know, you cannot simply bring the salt back to the sea. Because if you do like that, you concentrate the release of salt in a point at the local level, therefore producing pollution. So desalination is still a problem. Of course, desalination, as I mentioned before, it's potentially the final solution. Once that we got able to desalinate water, for instance, not through evaporation, but through filtering through membranes, with a low cost, and once we solve the problem of displacing the resulting salt, desalination has the potential to be, as I said, the final solution. And also keep in mind that most of the countries in the world have direct access to the sea. There are only, I think, 48 countries in the world that are landlocked, which means that they don't have any direct access to the sea. This means that desalination would be accessible to almost all countries in the world, which is, I mean, something really relevant. But for now, it is a future solution. It's not something that we can use now. Now, a second solution, besides increasing water supply, is water demand control and regulation. This is a solution that is increasingly practiced today. So it means that instead of increasing the supply, first of all, what is the problem? The problem is a mismatch between water availability, water supply, and water demand, where demand is higher than the supply. So one possible solution is to increase the supply. The second solution is lowering the demand. First of all, water demand can be lowered by controlling, by reducing the leakages, by reducing the water losses. And keep in mind that water losses are still very relevant. If you look at agriculture at the global level, the statistics say that half of the water is lost. Half of the water that is withdrawn is lost during the delivery for evaporation or for infiltration. I mean, strictly speaking, is not lost. You cannot lose water. Water is by definition renewable, but it doesn't reach the field, which means that the efficiency of the withdrawal is dramatically reduced. So if you look at the civil supply, where the water is delivered through pipes, pressure pipes, you may say by intuition that leakages, losses are less relevant. This is only partially true, because still in most of the aqueducts we have more than 30% of losses and leakages. Again, this is water that from the point of view of the supply, it's lost. Now, controlling losses is in fact recognized as one very promising solution for reducing the mismatch between demand and supply. And also there is the demand control. And the demand control, which is a different thing than with respect to losses, means that you are trying to reduce the demand for water by family people. And how to reduce it? Through, for instance, the use of smart taps, through pricing. Pricing has been shown to be a very effective way of reducing the water demand. And water price reforms can then be very useful. And also the controls on agriculture. For instance, if we live in a dry country like Italy, Italy is essentially, we cannot say in Italy that we have plenty of water. In the north of Italy, yeah, let's say it's fine, but we don't have abundance even in the north. In the south, we have water scarcity. So in a region like Emilia-Romagna, where water is available, but it's not abundant, especially during summer, and therefore we are forced to get a lot of water from groundwater. In a region like this, one should not cultivate kiwis, for instance, like they are doing in the past 10 years or 15 years, because kiwis are much water demanding. It is much better to cultivate cereals or other less demanding crops. Of course, if these crops, these highly demanding in terms of water crops, can be cultivated in other countries where water is more available. And then trading is an option to, through the virtual water trade, to compensate for this different agricultural production. So, of course, it is a complex system to regulate. It requires interaction between countries. It requires a continental approach. It requires concertation at the continental level, which, as you know, from the point of view of politics, it is something sensitive because, especially today, there are some people who see negative implications of losing sovereignty. You know that there is an increasing call to sovereignism today, which is motivated by good reasons. I'm not questioning that. But one has to be aware that getting independency, for instance, in agricultural production, getting sovereignty in agricultural production means that you lose the benefit given by cooperation, that in this case, from a technical point of view, it's clear. So we have countries with a lot of water, we have countries with less water, so why not establish cooperation, and a cooperation that has to be collectively more efficient in terms of water use. Of course, it's something that needs to be governed according to the principle of equity, democracy, and equality of opportunities, which is not easy. And the fact that it's not easy is the implication that brings some people to prefer sovereignty and independency. But as a technicians, we have to be aware of what is the solution, and the solution is through management of water resources that is more coordinated at the global level, with, of course, all the concerns that globalization may induce. But it is our duty to be objective again and focus on the sciences, and this is what the science tells us. Now, let me say that in the context of optimizing the use of water, it is compelling to study also the extremes, and in particular droughts. We need to be prepared not only to manage what is the current and the more frequent situation. We need to be prepared in advance against an extreme that may occur. And I want to give you an example that is very, 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 very significant today: the pandemics. Were we prepared to cope with the pandemics? Of course not. Did we know that the risk of the pandemic was significant? Of course, yes. We knew the risk, but we were not prepared. Let's move to water. Do we know that it may happen that a drought occurs and may last for 10 years in Europe? Yes, we know. Why do we know? Because if you look at the past records of climate, it is clear that Europe is prone to droughts like the Californian one, that occurred in the past decade, the Australian one that occurred from 2000 to 2010. So it may happen. Are we prepared to cope with it? No. And this is something that it's really important. And so to study the extremes and to be able to cope with the extreme is very important. We will have a lecture on climate where we will try to understand how to decipher if a climate is prone to extremes. It is a fascinating topic. It requires some maths, some statistics, but it's still fascinating because it gives to you, finally, the means to understand climatic variability and climate change. Just to give you an example, I mentioned to you a couple of droughts. So let me open a browser and show you how. I think there are these links in my web pages, but I just want to give you directly a suggestion if you want to get additional information. So if you say drought, if you look in Google for drought Australia and Wikipedia, because we jump directly to a source that is available and it is reliable. Wikipedia in English is reliable. Wikipedia in the native languages, you have to be careful. You see drought in Australia, Wikipedia. Let's open it. This is a full history of the droughts in Australia. Now, let's look at the drought in the 21st century. And here you see this link, Millennium Drought in southeastern Australia. Let's click on it. There is another Wikipedia page. This is what is called, let me expand the font. This is what was called the Millennium Drought. This was a very severe drought that lasted 10 years in Australia. And then it was declared closed in 2011. Now, I can imagine your question. Is this drought related to climate change? The answer is we don't know. We still don't know if global warming is increasing the risk of drought. If you focus on the science, the science says that we still don't know. We know that these droughts in Australia occurred in the past several times. In front of the question, are they now more frequent, getting more frequent under global warming? The answer is we don't know. Now, what matters here is that a thing like this may happen again, no matter climate change or whatever. Even if climate change was not increasing this risk is already huge enough not to be neglected. And what did Australia do? Usually they focused on desalination. And it is with the result that these desalination plants are now not used in the past 10 years. So, of course, it's something that we have to take into account, this variability, which brings us to focus on solutions that can also be maintained in the long term. Another example, let's go back to Google because it's interesting. Drought, California, Wikipedia. A similar issue. The droughts in California. California is known to be subjected to droughts, but from 2011 to 2017, they experienced a dramatic drought. And again, the connection with climate change is not clear. What is clear is that this is something that happened in the past. What is the reason for this for these events. We don't know. We don't know what is triggering these long-term cycles. And we just know that they may happen. Can they be predicted? The answer is no. We don't have now the knowledge to predict whether the next year, wherever you may think of, a long-term drought may start. Another question, are we prepared to that? No. And so this is something that is really a relevant risk that is unprecedented, because one thing is a drought 100 years ago. One thing is a drought now. It's the water demands are much higher. And so it is really a relevant challenge that for some reason is being ignored, like we ignored the challenge of a pandemics, even if virologists predicted that. They predicted that the globalization may trigger the widespread diffusion of global viruses, but we ignored it. You know, one reason why we ignored is that we had other priorities. Like now, the possible occurrence of a drought is something that may happen, but we have other priorities. Still, I think it is extremely risky that we don't try to predict this risk. Let me give you another example, and I go to my webpage to anticipate a lecture that I will give you later on related to climate change. And I just want to jump directly to a figure that is there, which is annual rainfall in Bologna. I think it is somewhere here. Let me see. I hope I'm not remembering. Here it is. So you see this picture. Let me bring it on the screen. This is annual rainfall in Bologna. In Bologna, we are lucky. We have a rainfall series daily. I'm sorry, it's in Italian. I will give you I didn't realize it, that the title of the axis were in Italian. I think you can understand. It's the x-axis is year, and the vertical axis is cumulative rainfall, which means total rainfall depth during each year. As I said, we are lucky in Bologna because this series was observed since 1813. And if you look at the series in gray, I identified, it is a figure that I drawn myself. I identified the long-term droughts, the droughts that lasted more than 3 years and produced a deficit which is more than 30% of annual rainfall, which means that the annual rainfall was for all the drought duration lower than the average of at least 30%. You see that a lot of droughts, a lot of long-term droughts occurred in the past, up to 1950. And now it's from 1950, 1960 that we didn't get any. But I mean, it's clear if you look at the series that a drought in the Emilia-Romagna region, a long-term drought, may occur even next year, even during 2021. Why not? And again, we are not prepared against it. Our water supply systems are not prepared to face this risk. Okay, this is about the extremes. Let me close this window and go back to my slide. And we will talk about this. Now, how can we, let me say a few words. Yeah, please.
There is a question in the chat.
I'm sorry, thank you. I was not visualizing the chat, so thank you for reminding me. Okay, in addition to building of reservoirs, surface water require more and expansive treatment techniques for biological, okay. Yeah. You know, the problem of groundwater, it's, okay, first of all, we understand that it depends on the situation at the local level, meaning that the use of surface water and the use of groundwater has different costs depending on the situation in the country. So we have seen the example in the slide before of California. Let me go back. Here you see that the surface water is maybe more costly than using groundwater. So it depends on the local situation. And this is a consideration that has to be done at the local level. If I look at my region, I tell you that surface water, even including the treatment, any kind of treatment which may be needed also for groundwater, because for instance in this region we have the problem of groundwater that is polluted by nitrates. So I mean treatment may be needed for both forms of water resources, but still in the Emilia-Romagna region, and I would say in most of the north of Italy, surface water is less costly. So from the economic perspective, my reply to your question is that you need to make an assessment at the local level. It may happen that groundwater is cheaper, and in this case, one may say, I don't see any problem in using it. Okay, but I also would like to say that you have to consider the sustainability of the use, because as I said, surface water is immediately renewable. After 1 year, it's completely renewed. Groundwater, it's a different story. So for instance, during a long-term drought, usual policy is to, given that you don't have surface water, because it's the first that runs out of during a drought, a possible solution is to use groundwater. On the other hand, if you use groundwater for 5 years, more than usual, it may need, I don't know how many, but possibly 100 years to get back to the previous situation, to recharge, which means that you have to be very careful in using it. This is another perspective. So we talked about the economic perspective before. Now I'm talking about the sustainability of the source. It's another perspective. And when you plan management of water resources, you have to plan by taking into account all of these information. You have also to take into account the costs that are needed to bring the water to the people. Groundwater usually is more readily available. Surface water, you need to deliver it. You have to also to take into account the possibility of experiencing an extreme, like I was just saying now, the extremes, the long-term droughts. I hope I replied to your question, and in any case, I just wanted to tell you, to remind to you, if thank you very much for reminding me about the chat. If it happens again, because you know I have two screens and sometimes I'm using both of them in order to deliver the lecture, and I cannot look continuously at the chat. If it happens again, please step in again. And by the way, I'm going to lecture for 15 minutes more, and then I make a break of 15 minutes before the next hour. Now, I want to introduce with a couple of slides what is the best way for managing the risk, for finding the solution to the problems from a technical point of view. Because now what we did is to identify the problem, to identify possible solutions. Now let me spend a few words how the solution is to be selected. So it's better to increase supply. It's better to reduce the demand. How can we make this assessment? So what is the framework of our analysis? As engineers, again, not as policymakers. If I was a policymaker, I would go to the engineer and I would say, please give me the technical information, and then to find the appropriate policy by taking into account the societal implication, etc., is my task of the policymaker, of the politician. But as engineers, what is the framework of our analysis? There are different approaches, and for instance, it was widely popular in the past 20 years to use the so-called top-down approach, meaning that with the top-down approach, you start from studying the climate. You may include the probability of extremes. You may include the climate change scenarios, and then the top-down approach makes a prediction, and then makes a prediction of what? Of the climate, of the risks, and then based on the prediction of the risks, finds the solutions. Now, this approach has the problem that you may end up with a solution that is not feasible. It's not doable. And this happens frequently. Frequently it happens that the policymaker, the politician, goes to the engineer and says, I have a problem of water scarcity. What should I do? Okay, and then the engineer, what he, she may do, what they may do, is to make a climate assessment, to make an assessment of water demand, make a prediction, and then say you need a very huge dam, because my prediction says that there might be the risk of a huge drought. My prediction says that there might be a climate change, and typically they sum up all of these risks and make a prediction. And then the answer is that you need a massive solution, a huge dam, something really demanding in economic terms, in terms of environmental impact, something really demanding if you want to take all the risks into account. And then what frequently happens is that the policymaker says, I don't have the resources to do that. It's too massive, too demanding. I don't have the resources. And then we are left with no solution, and the problems remains unsolved. This happens very frequently. I can give you different examples. Several examples. One example is the city of Florence. You may know that 55 years ago, in 1966, Florence was flooded. Okay. After the flood, they make some cosmetics to increase the conveyance of the river. But actually, in the past 55 years, people debated on what is the best solution for Florence. And it turns out that most of the solutions are not practical. They cannot be put into practice. Now, the result is that Florence is at the same risk of 1966. So if another flood like that one comes, Florence would be completely flooded, with the difference that the value of the goods, the exposure of people is much higher. So this is a situation that frequently happens. So this brought some researchers, starting about 10 years ago, to propose an alternative approach, the bottom-up approach. The bottom-up first identifies a solution to the current problems, an optimal solution. So it doesn't make any prediction on the future. It starts from the awareness that there is a problem. So there is a current mismatch between water supply and water demand. So we estimate the current mismatch and find the optimal solution to solve it, which means that at least we address a current problem. And then, as a second question, comes the question of whether or not the identified solution is resilient against the risks that we may predict for the future. The question is the identified solution resilient against a multi-year drought? Is the identified solution resilient against a prediction of climate change? So the prediction for the future comes after the solution has been identified, which means that if a solution is not resilient, then we may wonder whether another solution that is equally efficient is more resilient. So at the end, you use the prediction of the future to discriminate and to identify the most resilient solution among those that can be done. So this is for instance, one complication in Florence is that if we want to identify a solution that is resilient against climate change, we need massive interventions. So in Florence, I would like to say, let's start bringing the risk to an acceptable level with an optimal solution. Okay, The solution is practical. Let's adopt it. And then the question comes, is this solution resilient against a possible climate change? It's a different approach, which focuses on the solution. And you may remind the approach that I proposed for teaching, focusing on the solution and then find the best theory. I was inspired precisely by the bottom-up approach in risk management. Let's focus on the solution to current problems, and then resilience with respect to climate change, with respect to future predictions, comes later. This is presented in this figure, top down, bottom up. So top down starts from the future, predicted climate, and then it goes to solutions, to people. The bottom up starts from people, from the solution, and goes back. This is something that is becoming increasingly popular today. And I think that for an engineer, this is something that is really relevant. Again, this is not something that I will ask you at the exam, but you have to be aware of the possible approaches of, you have to be aware of your optimal workflow. Good, I think this presentation is finished. So let me back to the website and let me just get it back. Here it is. So we got to the end of our third lecture, Sustainable Management of Water Resources. Now I would like to make a break. And first of all, by taking the suggestion by some of you, I will not stop the video during the break, because otherwise there is the risk that I forget to start it back again. And so you will know that in the video you will have to skip these 15 minutes. Beware of not saying anything particularly compromising during the break. And I just would like to say that the next lecture is more technical. And instead of starting today with the next lecture, I would like now to introduce the exercises by introducing the software in the next hour, which means that in the next hour, I will start by asking you to install the software together with me. I don't have the software installed in my computer either, so we will need to move forward together. And this is something that is framed into my proposal to focus on resolving practical exercises and learning something about programming during our cooperation, during these lectures. This is something that I will not ask at the exam. And so if you are not interested, maybe because you are already very good in programming and you think that you don't need to expand your knowledge, you can skip these lectures and it's absolutely not a problem. My suggestion for you is to attend. They will be kind of 6 hours, so not much. And I think it is useful if you attended. But if you prefer, it's not a problem. It's just up to you. Now, I propose to make a break up to 15 minutes, and then I will see you back. So now I am just everything. I am sharing my screen and putting everything, stopping my micro and my camera. See you in 15 minutes. Do you have any question? I have the chat in front of me, so if you wanna ask me any question, please.
I have one, if I can.
Yeah. Please.
When you talked about the different climate classification, can you repeat the difference between B and D? Because I write down that both are dry climate. I don't think that is correct.
Yeah, but D is the cold climate. D like day is cold climate, which is not really, it's the dry climate, B like Bologna, is a very hot climate. So it's dry, hot. The D is cold, which may imply that it's also dry because water is highest. But in the cold climate, it's not water scarcity the problem. The problem is that in terms of food production, they are lands that cannot be used not for water scarcity, but for the cold climate. So this is the difference. And if you look at the map.
Thank you.
Okay, thank you. Any other question?
Good morning.
Yeah, please.
Morning. Okay, I'm Lee Vape.
Yes.
This is in response to the question that I asked within the chat. Yeah, thank you for your response. Okay.
Yeah.
I will want to believe that groundwater in my region is much lesser compared to surface water supply because we have a very shallow aquifer with a very good safe yield. But surface water, the source is far away from the city and contamination rate is high. So you have to treat the water, transport it about 4, 5, 6 kilometers to the city before distribution. But for the groundwater, you could just construct a borehole within a particular location and distribute. So that was what I was trying to look at in terms of local conditions. So thank you for your response.
Yes, first of all, let me say that it would be interesting if you could deliver a short presentation with figures and technical details to your colleagues. So consider it within what I propose to do in terms of interaction between me and you, because I am really interested in knowing local problems. And I think it is interesting what you said. And I think it emphasizes the need to collect information, plenty of information, all the valuable information at the local level before starting a design. It is, I mean, there is no general solution to water problems, but we need to find local solutions that are globally sustainable. So, I mean, the examples that you bring is extremely relevant because, you know, I was born in this region, in the Emilia-Romagna region, and I often say, I often mention my knowledge about this region, but, you know, there are so many possible scenarios. And it is, as I said, if you could deliver a short presentation, less than 10 minutes, it would be great. Just consider it. And okay.
Thank you.
Any other question? Okay, so let's meet back at 11. Okay, see you soon. Okay, here we are. I just would like to confirm that I would like in the next hour to start our first session of exercises. I just wanted to get to you. I just wonder if you have any comment on that. Okay, so now let me share the screen. if you look down in my web page, there is a section with the tutorial web pages for practical exercises. And here you see that the first link is Introduction to R and RStudio. And if you click there, you see that there is a presentation, 12 slides, which is introducing the package that I would like to use with you. And my suggestion is that you look at this presentation later. And for now, I would like to start from scratch, from the very beginning of this package. First, I would like to explain to you why I decided to use this package. Just 1 second, because I am trying to make sure that yeah, there is something wrong with the connection, I think, because just 1 second. Okay, let me share the screen. Can you please let me know if you can hear my voice, please?
Yes, we can.
Yes,
Okay.
yes. Hear your
Okay.
voice.
Yeah, okay, thank you. So the problem is the phone, because as I said, I'm checking with the phone that you can, just 1 second, I try to reconnect with the phone. Okay. Okay, and now let's see. Okay, good. Now I am okay. Now let me share the screen again. Okay, it seems that now everything is working. Okay, so as I said, I decided to use this package, and let me explain why, which is called R. I explain why by moving with another window to the website of the package, which is, let me show you. You can look in Google for R project. Okay, so if you check, if you search in Google for R dash, middle dash project, and then you get the first link. It's the R project for statistical computing. Forget about statistical. I will explain you later why it's called in this way. And you get to the web page that you can see here. So why this package? So first of all, we need a package for making computations, and the usual choice is Excel, or let's say an electronic sheet. One possibility is Excel. Other possibilities are LibreOffice, or there are other free softwares that are Excel-like. What is the main purpose of Excel? Making computation in a what you see, what you get environment. It means that Excel shows to you immediately on the screen what you are doing and the result. Can you please turn off the micro? Somebody has the micro open. Thank you. And so Excel is very user-friendly. It works with menus and windows. And again, it's extremely helpful because you see immediately what you get. Excel needs some training because you have to know what are the names of the various functions. Like, for instance, if you want to compute the square root, of a number, you need to know what is the name of the function that computes the square root. But let's say that the level of training is very low because, as I said, Excel is very user-friendly. What is the disadvantage of this? What you pay is in terms of flexibility. Excel is not very flexible, meaning that if you want to make a computation that uses the formulas, what is pre-programmed in Excel, what is presented in the menus, that's fine. If you need a computation that is not ready to use, you cannot find in the menus, Excel becomes more complicated. So if you want to customize Excel, it's a bit more complicated because, again, when you, for whatever package you use, if you want to make it user-friendly, you lose flexibility. It's like, it's like with a car. If a car is very driver-friendly, you lose flexibility. And but still, Excel is an opportunity. So many engineers work with Excel. What to do when you need more flexibility? If you need more flexibility, you need an alternative package. And an alternative package may be, I think that many of you have worked with MATLAB. MATLAB is a software that is less user-friendly. If you never experienced MATLAB, don't worry. You don't need to know what MATLAB is. You just need to know the concept. There are softwares that are less user-friendly. You don't see immediately what you get, but they are more flexible, and you can make programs with them. And so these softwares, I think, are an essential background for an engineer, because sometimes in your profession, you will need to solve problems that require a complex computation. So when the computation is complex, typically you cannot use Excel. You may use a commercial software, like there are many softwares that you can use to make computations related to structural mechanics. There are softwares that you can use to make computations related to hydraulic engineering. But what if you cannot find a software that it's ready to use to meet your purpose? And the reason that it's not ready to use may also be the cost of the software. And you may not be able to support buying a software that costs thousands of euros. So the solution is that if it's possible and feasible, you prepare the software yourself. It often happens in the career of an engineer to have a need to compile a program. And sometimes we are concerned like, this is very difficult. This is not true. It's not difficult to compile a program, to prepare a new program, with the advantage that you know what the program is doing. If you use a program that is already prepared, you don't know what is behind the result that it is presented to you. And take into account that you are legally responsible for it, which means that if you know what you did, you are much safer. Of course, when it's possible to use a program that is already set up, we shouldn't decline this opportunity. But our choice has to be informed, meaning that we need to know what is available. We need to know what we can do from by creating a new program. We need to know what is the effort required, because at the end of the story, at the end of the day, our objective is to be, our purpose is to be very efficient. And in order to be efficient, we need to know how to select the best way to work. And in order to make a selection, we need to know the different solutions that we can put into practice. So all of this introduction is to tell you, don't be concerned by programming. Get the background that is needed to make a program, to elaborate your own program, so that you can understand when something is possible, when something is convenient, and when it's not. if you don't know, if you don't learn how to make a program, if you don't learn how much it's difficult to make a new program, you cannot make a choice. So in order to prepare your CV, in order to have a successful and happy career, my suggestion is learn what is a program, learn how to program. So as I said, maybe that some of you already experienced MATLAB. MATLAB is an excellent solution. It has only a disadvantage that it's commercial, which means that you have to buy it. In the university, you can use it because we have a campus license. But once that you are out of the campus, you cannot use it. And once that you are graduated and you are not anymore a student at the university, you have to buy it. It's not very expensive. It depends on the package that you buy, but still it is commercial, and it requires some trust in the brand, and the trust in the fact that it's a knowledge that is not going to expire. So my suggestion is, in any case, to find a different solution. And in my opinion, an excellent alternative to MATLAB is the package that I'm showing you on the screen. This is a package that is open source. It means that it's freely available, and it is supported by a community of users. It's not commercial. There is no one paying for it, and there is no one getting a salary for keeping it updated, but its strength is the size of the community, which means that you can find a lot of already prepared programs. You can find a lot of support if you want to get a problem solved. And so, as I said, in my opinion, it's an excellent alternative. It started as a software for statistical computing. Now it's a general computing software, not only statistical. The word statistical can be dropped out. And I want to say this because some students, when they see the word statistics, they get concerned, like something that is very difficult. It's not. So it's just an open source software that you are free to use. So I say, why not? Let's try to make our experience with this. The first thing that we have to do is to install it. It's not installed in my PC, and my PC today is a Windows PC. Usually I'm not a Windows user. Usually I am a Linux user, and I will explain to you later what are the operating systems that you can use. But basically most of people use Windows, and the most known alternatives to it are Mac and Linux. Mac is, I think some of you may have a Mac. I don't think some of you are Linux users. If yes, please let me know. Just write on the chat or send me an email if you are a Linux user, because it's important for me to have a perception of what kind of users I have in front of me. I think maybe you are now 14 students. I would say that probably 2-3 of you may have a Mac, and the others have a Windows PC. As I said, usually I am a Linux user, but today I got a Windows PC because I wanted to put myself in the same condition as most of you are. So in front of a Windows PC with no R installed. So I think we can go through the installation together. Before I move forward, do you have any questions so far? I'm looking at the chat. It will take about 10 minutes to install everything. So I think we can start if you don't have any question. And by the way, if you can't follow me for some reason, you have two possible solutions. Either you let me know if the problem can be solved by just waiting or discussing together. Exercises are an interactive exercise. And so don't worry to stop me if we need to discuss what you say. Your questions would be useful for the other students. Or you may be in the condition that you cannot follow me because for some reason you cannot install in your PC a new program for some reason. If you are in such a condition, I don't think it's a problem. You can just look at what we are doing. You have the video later, and if you may install later the program, just get aligned before the next lecture. And if you instead don't have any possibility of installing a new program, just let me know, and you will be required just to attend to look at what we are doing. I think you are not losing much. Of course, if you practice, it's a more useful exercise. So if there is any problem, just let me know on the chat or stepping in with the micro. So I think the first thing that we have to do is to download it. So if you look at download, let me expand the font. Okay, download, there is a link, CRAN. You can just click on this without wondering what is CRAN. It's not a problem. And then you have to select a mirror. It doesn't matter. You can choose whatever mirror you want. In the past, we were used to get suggested to choose the closest mirror because, you know, the network was not, the web was not so efficient. Now it doesn't make a difference. Usually, given that I was suggested 20 years ago to choose the closest one, usually I click on Austria 1, but it doesn't make any difference. And you get to this page, whatever link you clicked on. And so here you see the download for the 3 different operating systems, Linux, Mac, and Windows. Of course, you have to click on the operating system that you have. So I assume I have Windows, so I click on it. Okay. And then you get to this new page. You have to click on Base. This is the only package that we need. If you click on Base, you get a new page. Be patient with the clicks. And you see here, download R for Windows, 85 megabytes. Let's click on it. Okay, and I would say I click on Save File. Sorry, it's in Italian, my PC. Save File. And now it's downloading. I am using as browser Firefox, so I see the progress of the download in the taskbar. And if I click on the blue arrow now, I see the executable here, and I click on it. Now, at this point, I hope that you are in line with me. If there are some problems, just let me know. Now I'm getting a message that is not shown in the screen, which asks me if I wanna really install it, and I answer yes. Now I get the language to use during the install. I choose English because I want to use the version that also you will use. Okay. Let me click on OK. Before I move forward, I hope that you could follow me. The only thing I am doubtful of is if you could find the executable, because I clicked on the arrow in my Firefox browser to get it. And if you don't find it, just let me know. Now I click on the OK for the language. I accept the license. Next. And then there is the selection of the directory. Fine. Next. And then you see that there is the selection of the packages you want to install. I get a question on the chat, which is, I have RStudio installed before. Is it the same program? Yes, I would say yes. It means that in order to install RStudio, which I will install as soon as I finished here, because I want to use RStudio with you. In order to install RStudio, you previously installed R. So it means that you already have done this step on your PC, so you can skip it. I hope it's clear. So just wait for me. If you have RStudio, you just have to wait that we install both R and RStudio. Is it clear? Okay, now, as I said, there is this window with a pre-selection. Select the components you want to install. Let's select all of them. Next. And then customized setup or defaults. Let's take the defaults. Next. And then the program shortcut in the start menu folder. Let's take the default. Next. Again, select additional tasks. Let's take the default. Again, let's press on next. And now it's installing. Let's wait a little bit. Okay, click Finish to exit setup. Finish. Good, I am done. Now, before installing RStudio, let's open R alone. RStudio is a working environment that uses R in order to make computations. But I think that before installing RStudio, if you don't know R, it's much better if we make some preliminary training with R alone. So how to start R alone? I go on the task selections button. Let me see if, yeah, now you can see it. And I should find here R. You see that there is recently added R with two icons. I select the 64 bits one. And here I am, just let's wait. Okay, here I am. Now, I wonder whether you are in line with me. Any problem? So if you have this window open and you see on my screen, we can maximize it. And let me also increase the font. So it's, I think it is here under preferences and yeah, size. I put 14. Okay. If you are in line with me now, with this window open, you are okay. And if you are not, it may be that you need some more time. It may be that you experience some problems. If you want to share any problem with me, just take this opportunity to write on the chat or to step in with the micro. Can I take this opportunity to ask you if some of you already used R before? Just put on the chat, please, yes, if you use it before. Waiting for your reply. I think Wham, you used it before because you have RStudio installed, or maybe somebody else installed it for you. Okay, Abdelnour El Khatib, yes, perfect. Wham Hakim, yes, okay. I think the statistics is what I expected. 2 out of 14. Let me know how many we are. 16 now. Okay, 2 out of 16. This means that these two persons, you have to be a little bit patient the first hour, okay? So today and maybe the next one, because probably I will I am starting from scratch. And therefore, probably you already know some of the things that I am saying. Okay, so I assume that you are in line with me. So how to use R? You get in this window a console. What is the console? It is a terminal waiting for an input. You see this major or greater sign there. It means something like, I am ready to get your input. Very good. Of course, we need to know what language to speak with this guy here. And we need to know the instructions that the software is accepting. I cannot write something that it doesn't understand. And this comes along with training. Before I start the training, let me go back to the main page of R. Here we are. Now, let's look on the left, documentation manuals. I click there. Here you see manual, an introduction to R. This is extremely useful. So if you wanna get some support for training, I suggest that you download this. And you can just focus on R release. For instance, I open the PDF, and here you see this guide. It is quite a short guide. It's 100 pages, but really most of it, the interesting part is the first pages. So introduction and preliminaries, and the simple manipulation, numbers and vectors, etc. So I'm not focusing on it now. I'm starting from the very beginning. I just wanted you to know that this introduction may be a very useful way of improving your skills with R. Now let me go back to the console. So what commands R understands? First of all, you can make simple computations, 2 + 2. You press return and you get 4 magically. Okay, so this is one thing. You can also make any kind of operation in sequence. 2 + 2 × 6. What is the result here? What we are expecting is that it makes the multiplication first. So it's 6 × 2 is 12, plus 2 is 14. Good. So look at the priorities. Multiplication and division have the priority over addition and subtraction. If we want to give priority to the addition, I had to write this in this way, 2 + 2 × 6. And then I am expecting 4 × 6, 24. You can use parentheses as you like, as many of them. It's no problem. Just 1 second, because I got a message here. Okay, no problem at all. Good. Just 1 second. Good. So it's the for operation, but not only the for operation. You can also use powers. 2 to the power of 3 is 8, and the at is the power sign. Okay, which has the priority. If you make 2 + 4 to the power of 2, we get 18. But you can also use the parentheses if you have doubts on the priorities. Look at what I did. I wanted to recall the previous instruction. I used the arrow up. So with arrow up, I can recall back all the previous instructions. It's very useful because it gives you a way to save time. Okay. Now let me clear the screen. Ctrl + L. Good. So R has, like Excel, some functions. So if I want to compute the square root of 16, I can elevate it to the power of 0.5, which is okay. But I can also write sqrt 16. 4. So sqrt is the name of a function that computes the square root and look at how I wrote it. I gave the argument of the function, the number to compute the square root, between round parentheses. So R has some function embedded. Any function takes one or more arguments. Arguments are to be given between round parentheses. And you may say, how can I learn the names of the functions? You have two options. For instance, let's suppose that I want to compute the logarithm on base 10. I don't know what is the name of the logarithm with base 10 in R. How can I do that? How can I learn the name of each function? For instance, the sin function. What is the name? I have two options. First option is to look at the introduction to the document that I introduced to you before. But much easier is to do like I'm doing now. Suppose that I want to know the name of the logarithm base 10. So let me go to a web page and let me go to a Google page, google.com. Okay, here I am on Google. Now, what is my question? Logarithm base 10. So let me use this key for the search, R project, and then logarithm base 10. Okay, let's get the first link. And you see logarithm and exponentials, usage. Look here. I can use a function called log. Let me expand it. Which takes two arguments. The first argument is the number to compute the logarithm on, which is x. The second argument is the base, which has a default. You see that there is a default here, base equal to, what is exponential 1? First, I can learn from here that there is a function in R called exp to compute the exponential of a number. Exponential 1 is e. It's the number e. So here, I read that the default for the base of the logarithm is base e. If I want to give another base, I have to change this argument. So let's translate into practice. I go back to R. I learned that I have to use log. If I compute log 10, what outcome are you expecting from here? Look, I gave only the first argument. The second argument I'm not giving, which means that the program will take the default. The default is e. So I am expecting here the computation of the logarithm with base e. Perfect. The result is precisely what I expected. If you want to try exp 2.302585, I am expecting what? 10. You see, it's about 10. But then, if I want to compute the logarithm in base 10, what should I do? I use the arrow up, and I go back to the instruction to compute the logarithm, and I correct it. I add the second argument, base equal 10. Perfect. I got to target. Before I ask you if you have any question, let me go back to the help page that I found in Google. And if you look here, you see that there is already a second function that computes the logarithm. It looks like in base 10. So instead of using this function here, I may try to use log 10, 10. Questions? Because I introduced in 5 minutes a lot of things. I introduced functions in R. I introduced how to look for a function. I introduced the argument of the functions and their defaults, if any. Questions? Okay, I assume that you are in line with me. Way you can search for help for whatever function. Our project, scene, for instance, function. Trigonometric function, R documentation. You click here and there is a list of all the trigonometric function. Cos, sin, tan. So let's make a trial here. I clear the screen like sin pi. It's 0. What is pi? Pi is the number pi. It's already embedded into R. Cos pi. -1. Tan pi. 0. Cotan pi. Cotan is not there. What is it's I think it's tan atan. Atan pi. Yeah, I don't think this is not what I was expecting. I think it's because the tangent is fine. It's 0 because it's 0 the sin. And I was expecting the inverse of the tangent would be, I am expecting infinity. So let me compute it in this way for now, because I don't recollect what is the name, the direct name. And this is infinity, you see. Okay, so this is for functions. Again, if you have any questions, stop me. I still have 5 minutes to go, so not much. So we are not getting much further than now. And I now want to introduce how to define variables. And if I have time, vectors. I also would like to give you an homework, if you not to be delivered the next time, but just an assignment, just to have a look at the document, Introduction to R, whose link I gave to you. And let's say before, I'm not sure if Monday next week we will dedicate another hour to exercises. I would say yes. It depends on what we do on Thursday, and on Thursday for sure not. So if you could have a look at the Introduction to R, the first pages up to variables and vectors, okay? If you go back to this document, which I already closed. Let me see, just 1 second. I go back to the document, our project. Here we are, and here there is the documentation manuals, PDF, okay? And if you could read the introduction and preliminaries and simple manipulations, numbers and vectors, it would be great, okay? If you could just have a look, and if you don't understand something, don't worry, just leave it, because we will go through this together, okay? Up to page 12. By next Monday, if you could get a look, it would be great, okay? Now let me move forward with variables. So far we dealt with numbers. Variables are an opportunity. A equal 10. Here I defined a variable which is called A, whose value is 10. So if I now write A times 2, you get 20. So you can define variables. And you can also define another variable, b equal 2, and then write A times B, like numbers. The good thing is that you memorize them, okay? And if you want to have a list of the variable, there is a function called ls that you can use. And you see that it gives to you a list of the variables. If you want to know the value of the variable, you type A and you get the value back. Variables can be removed if you can overwrite them. So if you write A equal 20, then if you type A, you have the new value, or you can remove that RMA. Now, if you make ls, sorry, one, you now get only B. Be aware of the fact that the RM function cannot be undone. So I cannot get back the original value of the variable A, which means that you have to be very careful when deleting something in R. It has the advantage R that you can repeat the previous instructions with arrow up. So you can go back to the instruction with which you defined A. This is a way for undoing something. But it is not, rigorously speaking, an undo. It's a rebuild of what you, by mistake, perhaps deleted. You have to be fully aware of the difference. So there is no undo, strictly speaking, which means that it's much better if you save your status of the program, if you save your variables. In particular, there are two things that are worth saving in R. The first is the history. The history, which you can get back with arrow up. You see that I am pushing arrow up now. I'm getting back all the instructions that I used since the beginning today. This is extremely important and useful, because if you want to repeat something that maybe you erroneously deleted, this history is a great opportunity. You can have a look at the whole history. If you write, I cleared the screen up. If you write the function history with double parentheses, no arguments, and you see that you get the whole history. It's not really the whole history, because only the last, I don't remember how many, I think 20 instructions are given here on the screen, but actually the full history is kept into memory. Now, and the second thing that you may want to save is the variables. How to save history? Now, first of all, independently on your platform, you may save everything by quitting. Quit, the program, can be obtained with the function Q, with no arguments. And then if you press return, you get a question, would you like to save your working space? If you press yes, like I'm doing now, let me press yes, you get out from the program. But if I get it back by clicking again on the applications, and let me expand it, and let me again put the font to a larger value. If you look at now the new window that you opened, and you make a list, you have A and B. And if you go back with the history, you still have it. So this is a way to save both history and variables. You get out from the program and you save everything. On the other hand, if you don't want to get out from the program, you can use the instruction. I think the name is save history to save the history, but I don't remember it. So let me give you another suggestion how to get the name of a function if you don't know it. I guess it starts with save, but what is the full name of the function? Let me press tab twice, 1, 2. It gives to me all the alternatives that are having memory. Very good. So I can see that it's save history. I saved it. Keep into account that with Mac, the instruction may be different. Be aware of that. And if you can't find the way, just look on Google. Second thing, I want to save the variables. Again, save, double tab, save image. Save image. Double tab, I complete it. Done. I saved both the history and the variables without getting out of the program. Okay, I think at this stage, what I can do is quit everything and exit from it. I save my working space and we are done. And so I think that, just 1 second, because I have the phone ringing and I need to shut it up. Very good. I don't know. Okay, let's forget about it. Sorry. Okay, so here we are. I think we can now close the lecture. And I would say, I wonder if you have any question. Let me share the screen. Okay, it looks like you don't have any questions. So let me thank you very much for your attention. I hope that the lecture was fine enough. And we see each other once again on Thursday at the usual time, online only. Yeah, please, if you have any question.
Okay. Thank you for the presentation. Yes, I would really appreciate were you to have a 15 or 20 minutes introduction for the next class time. We appreciate at least to overview what you have done, please.
Sorry, can you please say again, because I couldn't get your voice well. Now it's fine. Could you please repeat? You would appreciate to get 10 or 15 minutes for what?
Yeah. Review, overview of what you just did for the next class time. Okay, that's fine. I mean, I can. Do you mean the part related to the exercise, or related to the R Studio? Yes, I need to. R Studio is still to be introduced. So I guess that you are meaning to review what I did with R, correct? Yeah, R. Yes. Okay, perfect. I think it will be sometime next Monday. Okay, I can do that. I can make a brief recap. Yes, next Monday. Okay, perfect. But meanwhile, we are meeting on Thursday for 2 hours, 9:15, 10:45. Okay. Thank you very much, and see you next time. And if you have any question meanwhile, you can contact me. Thanks a lot. Bye-bye.
Thank you. Goodbye.
Goodbye.